10.2 Areas of trapezoids, rhombuses, and kites. The objective in this lesson is to find the area of trapezoids, rhombuses, and kites. Now, this might be a good time to get out your classification chart from Chapter 6 in case you need some of the properties of these. Okay, let's look at our first theorem here. Once again, height is a perpendicular distance between the bases for a trapezoid. It might be worth noting, again, that height is always perpendicular. All right, so our first theorem is the area of a trapezoid, and we know that the area of a trapezoid is half the product of the height and the sum of the bases. So here is our formula, and if you remember from our definition, our bases are the parallel lines. That's definition of trapezoid. And we measure height perpendicular between those two bases. Now, I know that you're looking at this and telling me, well, this area is not base times height, but it most certainly is. And I want you to look at this. There's our h, right, for height. Base 1 plus base 2, okay, we take those and we add them together. And then we divide that by 2. That's where the 1/2 comes from. So we are taking the average of our two bases. Now, if we go over here to our bases, we have a long one and a short one. And let's imagine that I take half of this piece of the long base, and I take the other half and I put it up here. Notice how I take this little triangle piece and just flip it up. And then I take half, if we go down here, take half on this side, and I put it up here. Notice I now have a rectangle because I have found the average length of my two bases, and I now have a rectangle, so I am actually doing base times height. Now, you don't have to do this to solve it, but this is why everything is base times height. We are taking the average of the two bases and multiplying it by the height. But all you need to know is the formula there. Now let's look at an example of this. What is the approximate area of Nevada? Well, Nevada looks an awful lot like a trapezoid. First, we need to find our bases. These would be our parallel sides. So we're going to label base 1, base 2, and then this right here is going to be our height. So we have all of our numbers. We simply write our formula, plug them into our equation, and the area of Nevada is about 110,600 miles squared. Don't forget, the unit for area is always squared. And it's already your turn to try a problem. Go ahead and pause the video and give it a shot. That was almost too easy. We wanted to know the area of a trapezoid with height 7 centimeters and bases 12 centimeters and 15 centimeters. I drew my diagram, labeled my base 1, base 2 height, wrote my formula, and substituted in. Don't forget that base 1 plus base 2 is in parentheses. You must solve your quantity first. So 12 plus 15, and then just did the math. The area of this particular trapezoid is 94.5 centimeters squared. Do not forget your units. I will count you off on that. So that one was easy. Let's look at our next example. We want the area of trapezoid PQRS. So we are told we have a trapezoid. So we know we are looking at base 1, base 2, and uh-oh, where's the height? We are not given the height. But what do you see, right? The height would be right here, measured perpendicular. I see a special right triangle. So we have, there's a right angle. That measures 60. That means that's 30. That means we've got x, 2x on the hypotenuse, x root 3 on the long side. And we know that this is 2 meters. So that tells me this is 2 times 2, 2 times x. This one is 4 meters. That's not the one we want though. This, x is 2, I just substitute in, is 2 root 3 meters. So I know my height. So I now have base 1, base 2, and 2 root 3 meters for my height. Now, how did we get the side of our triangle is 2 there? Well, when we put our height down, we now have a rectangle, 5 meters on top, 5 meters on the bottom. This is 7 minus 5, gave us the 2 meters. I have all my pieces. I substitute in. 7 plus 5 is 12. So this is just 1/2 times 2 times 12 times square root of 3. Right? 1/2 times 2 times 12 makes 12. And then I just put my square root of 3 on there. The area of our trapezoid is 12 square root 3 meters. That is in simplest radical form. Now, if we were asked to find it to the nearest tenth, we would simply put 12 square root 3 into our calculator, and that would tell us that this would also be 20.8, because I round up, meters squared. So we can do that in simplest radical form or to the nearest tenth or nearest hundredth, whatever we're asked for. All right, guess what? Your turn. Pause the video and do the next problem. This problem was a little bit more challenging than the last one, but still not too bad. It said, suppose our trapezoid from up above, your height is decreased so that the measure of angle P there is now 45 degrees. Still going to be one of our special right triangles. All of our others stay the same. So now I still have my same base. Base 1 is 5, base 2 is 7. My height still comes down. It's still going to make the little piece of this triangle 2 meters. But now I have a 45, 45 right triangle. That means I label it x, x, and x root 2 on the hypotenuse. I know this little bottom piece here is 2 meters. So that means x is 2. That means my height is 2 meters. And I can do my hypotenuse is just substitute in 2 root 2 meters. That means nothing to us, but it doesn't hurt to label everything. So I now have base 1, base 2, and a height. Throw it in my formula, and the area is now 12 meters squared. So that was good. All right, that's trapezoids. You just label everything you know, write your formula, substitute in. And yes, you will be using all of our tools from Chapter 8. Okay, moving on. The area of a rhombus and a kite depend on the length of the diagonals. So let's take a look at our first theorem here. I guess it's our only theorem here. the area of a rhombus or kite. This says the area of a rhombus or kite is half the product of the length of the diagonals. Product means multiply. 1/2 diagonal 1 times diagonal 2. Now, I know that you're saying, well, that's not base times height. It is. Let's take a look at our kite over here. This diagonal, right? We have that diagonal. Now I want you to look at this triangle on the bottom made by our other diagonal. If I take this triangle on the bottom and flip it up, so I took this triangle right here and I flipped it up to the top. Now I'm going to take this triangle right here and flip it up here. I have a rectangle now that has a base that is the length of diagonal of this diagonal and a height right here that is half the length of my other diagonal. That's where our half comes in. 1/2 of this diagonal times this diagonal. So you see this is still base times height. You don't have to do that because we have a formula that does that for us. I just wanted you to see that it's still base times height. All of these figures are just made out of a rectangle. A base times height rectangle. All right, let's do an example here and see what we're doing with this. We want to know the area of kite. We have a kite. KLMN. What do we know about kites? Well, on this one, all we really care about, we'll get to that in a minute. Here's diagonal 1. Diagonal 1, what does it measure? 2 plus 5. So that is going to equal 7 meters. And then here is diagonal 2. What does diagonal 2 measure? 3 plus 3 is 6 meters. So I have diagonal 1, diagonal 2, write my formula. 1/2 of 7 times 6. 21 meters squared. Don't forget your units. Apparently, it's your turn again. Go ahead and pause the video. Do the next problem. That problem was almost too easy to actually have to do. It said the area of a kite with diagonals that are 12 inches and 9 inches long. I drew my kite. I have a diagonal 1, it's 12 inches. Diagonal 2 is 9 inches. I write my formula, substitute in. 1/2 times 12 times 9. That's 6 times 9 is 54 inches. And yes, it is squared because it is area. All right, let's move on to our last example here. This is going to be an example that you want to pay attention to and remember because it uses a lot of good stuff. These are the diamonds that are painted on the roadways. And these are rhombuses. That means all of our sides are congruent. We know this is a rhombus, so all of these sides are congruent. And we are given these measurements. This side here is 6.5 feet, and this side here is 2.5 feet. Well, if we are interested in the area, we want the lengths of the diagonals. So let's draw in the diagonals here. We want those lengths. Well, we know this length and that length. And what else do we know about rhombuses? We know that our diagonals are perpendicular. So that is really a useful thing for us. So what I see happening here is we have a right triangle. We know that this side is 2.5 feet. We know that the hypotenuse is 6.5 feet. And we need this information here. We also know about a rhombus that the diagonals bisect each other. You remember that? That's a parallelogram thing. So we can say that this side is 2.5, this side is also 2.5. So we know that we'll call this diagonal 1 is 2.5 plus 2.5, so diagonal 1 is 5 feet. We need diagonal 2. How are we going to do that? I have two sides looking for the third. That sounds a whole lot like the Pythagorean theorem. So we use a squared plus b squared equals c squared, and so c, a, b, x squared plus 2.5 squared equals 6.5 squared. We end up with, doing the math, x equals 6 feet. So we can now label this 6 feet, which means this is 6 feet. So diagonal 2 is 6 plus 6 is 12 feet. And then it's just a matter of doing the math. So our roadway diamond, which is a rhombus, has an area of about 30 feet squared. And it is your turn to do the last problem. Pause the video and enjoy. All right, if you paid attention in the last problem, this one was pretty easy. We're given a rhombus with sides that are 10 centimeters long. We know all of our sides are 10 centimeters. I just drew my rhombus. And the longer diagonal is 16 centimeters, so I knew D1 is 16 centimeters. We want the area, so I know I want D1 there. And so I want diameter 2. So I draw in diameter 2, and we don't know what diameter 2 is yet. But I do know that on a rhombus, my diagonals are perpendicular and my diagonals bisect each other. And I see a right triangle right here. So I redrew my right triangle. I know that my hypotenuse is 10 centimeters. I know that my leg on the left there is half of the entire diagonal, so that's 8 centimeters. And then I am looking for the bottom leg. So ABC, Pythagorean theorem, I find out that x equals 6. So I have 6 centimeters here. I know that this is 6, and I know because my diagonals bisect, this is also 6. So diagonal 2 is 6 plus 6 is 12 centimeters. I now have two diagonals. The area of my rhombus, 1/2 D1, D2, do the math, comes out to be 96 centimeters squared. Easy problem if you pay attention. Draw your diagram, label everything you know, have your Chapter 6 quadrilateral classification chart out in front of you, have your Chapter 8 knowledge out in front of you. We've used the Pythagorean theorem and special right triangles so far. Don't worry, trig is coming. And use your right triangles to find missing lengths, and then it's just easy using your area formulas. So we actually have 3 area formulas, but 2 of them are same. Rhombuses and kites use the same formula. So if you are careful, I know that you will find these problems to be very easy to do, and you will have fun on your homework.